About the group 17 elements. The group 17 of the periodic table contains the elements fluorine, chlorine, bromine, iodine and astatine. They are collectively known as halogens. The halogens are highly reactive non-metallic elements and show greater similarity amongst themselves. These elements are highly electronegative and form anions which constitute the part of salts found in the seawater. Astatine is a radioactive element. The valence shell electronic configuration of these elements is Ns2Np5. For example, the valence shell electronic configuration of fluorine is 2s2 2p5 and that of chlorine is 3s2 3p5. These elements are highly electronegative, that is, they have the stronger tendency to attract electron towards itself, since they require only one electron to attain the stable electronic configuration. Thus, halogens are highly electronegative in nature. Next, we will discuss about the occurrence of halogens. Fluorine and chlorine are fairly abundant while bromine and iodine is less. Fluorine is present mainly as insoluble fluorides, example fluorspar, that is CaF2, cryolite, Na3Al6 and fluoroapatite. The small quantities are present in the soil, river water plants and bones and teeth of the animals. Seawater contains chlorides, bromides and iodides of sodium, potassium, magnesium and calcium, but is mainly sodium chloride solution, that is 2.5% by mass. The deposits of dried up sea contains these compounds, example sodium chloride and carnallite. Certain forms of marine life contains iodine in their systems. Various seaweeds, for example, contain up to 0.5% of iodine, and Chile saltpetre contains up to 0.2% of sodium iodate. The important atomic and physical properties of group 17 elements are given here. Next, we will discuss about the physical properties of halogens. Fluorine and chlorine are gaseous at room temperature, bromine is a liquid and iodine is a solid. In the elemental state, all the halogens exist as diatomic molecules. The atomic and ionic radius increases from fluorine to iodine due to the increase in number of shells. Halogens have little tendency to lose electron. They have very high ionization enthalpy. Due to the increase in atomic size, ionization enthalpy decreases down the group. Halogens possesses low melting point and boiling point. The melting point and boiling point increases on moving down the group due to the increase in atomic mass. Halogens have very high electronegativity. The electronegativity decreases down the group. Fluorine has got the greatest electronegativity, followed by chlorine, bromine and iodine. The high value of electronegativity of halogens are due to their small size, atomic radii and high effective nuclear charge. The electron gain enthalpy of the elements of the group becomes less negative down the group. However, the negative electron gain enthalpy of fluorine is less than that of chlorine. It is due to the small size of fluorine atom. The density of halogens increases on moving down the group. All the halogens are colored. This is due to the absorption of radiations in the visible region, which results in excitation of the outer electrons to higher energy levels. By observing different quanta of radiation, they display different colors. For example, fluorine is yellow, chlorine is greenish yellow, bromine is red, and iodine is violet in color. Due to the higher value of electronegativity, all halogens are typically nonmetals, and the nonmetallic character decreases down the group. Halogens have the outer electronic configuration Ns2Np5. Hence, these elements tend to gain or share one electron to attain the stable electronic configuration of Ns2Np6. Hence, these elements show the -1 oxidation state. That is, the halogens require only one electron to attain the stable electronic configuration. So, by accepting that one electron, the charge of halogens become -1. Fluorine is more electronegative and shows only -1 oxidation state. Fluorine, due to its small size, the attractive power of the nucleus to attract the electrons towards itself is very high. Thus, fluorine is highly electronegative. Other elements exhibit positive oxidation state of +1, +3, +5 and +7. These oxidation states are possible by the excitation of the outer s and p electrons into d orbital. The 3, 5 or 7 unpaired electrons are made available for bonding. All the halogens are highly reactive. They react with metals and nonmetals to form halides. The reactivity of halogens decreases down the group. Here we can see that the halogens in the ground state, first, second and third excited states, it can form 1, 3, 5 and 7 unpaired electrons respectively. More the number of unpaired electrons, more is its ability to form chemical bonds, and thus halogens are highly reactive. Excitation means after receiving the required amount of energy, an electron in a particular energy level jumps to the higher energy level. The concept of excitation can be explained with the help of carbon. The electronic configuration of carbon is 1s2, 2s2, 2p2. It has got only 2 unpaired electrons. That is, it can make only 2 bonds right now. If the carbon want to make 4 bonds, as in the case of CH4, it requires 4 unpaired electrons. For that, one of the electron in 2s orbital is excited to 2p orbital by accepting energy in the form of photons. All halogens react with metals and many nonmetals to form halides. The reactivity decreases down the group from fluorine to iodine. All the halogens react with hydrogen to give hydrogen halides, but the affinity for hydrogen decreases from fluorine to iodine. The stability of these halides decreases down the group due to decrease in bond dissociation enthalpy in the order HF greater than HCl greater than HBr greater than Hi. Stability means the bond strength between the halogen and hydrogen. In HF, both hydrogen and fluorine are small atoms and hence the nuclear attraction is very high. Thus, the stability of HF is very high. On going down the group, the atomic size of the halogens increases. On increasing the size, the attractive power of the nucleus decreases and hence the bond strength also thereby decreases. Thus, the stability of the halides decreases down the group. In HF, that is hydrogen fluoride, due to its small size and high electronegativity of fluorine, it shows hydrogen bonding. On the other hand, other halogens do not show hydrogen bonding due to the larger size and low values of electronegativity. The variation in properties of hydrogen bonding, melting point, bond length and bond dissociation enthalpy is given here. Bond dissociation enthalpy means the energy required to break a bond between two atoms. In HF, due to the small size and high electronegativity of fluorine, the bond strength is very high. Thus, HF has got the highest bond dissociation enthalpy and followed by HCl, HBr and Hi. Owing to the small size and high electronegativity of fluorine, HF is the most thermally stable among all the hydrogen halides. The thermal stability decreases in the order HF to Hi. HF does not show any reducing character, but Hi is a strong reducing agent. The reducing character of the hydrogen halides increases from HF to Hi. The agents which can donate electrons are called reducing agents. The atomic size of the halogens increases from top to bottom. Due to this, the bond length increases. This means that the bond length of HF will be less than that of Hi. As the bond length increases, the bonds can be broken easily and thus it can donate electrons. Due to the above mentioned reasons, the reducing character increases from HF to Hi. Halogens react with oxygen to form many oxides. Most of the oxides are unstable. Halogens show tendency to react with metals and form metal halides. Fluorine reacts spontaneously with water and oxidizes water to form oxygen. All the halogens react with hydrocarbons, but the reactivity decreases with increase in atomic number. Fluorine reacts spontaneously with alkali giving fluorides, oxygen and water. For example, 4 molecules of sodium hydroxide react with 2 molecules of fluorine to give 4 molecules of sodium fluoride, oxygen and 2 molecules of water. Fluorine and iodine does not show bleaching action. Chlorine is a good bleaching agent, whereas bromine show slow bleaching action. The bleaching action of chlorine is due to the formation of nascent oxygen given by hypochlorous acid. Nascent oxygen means atomic oxygen which is responsible for the bleaching action. Bleaching can be defined as the process of whitening a fabric by removal of the natural color. Bleaching is usually carried out by means of chemicals selected according to the chemical composition of the fiber. Chemical bleaching is usually accomplished by oxidation, that is destroying color by application of oxygen. Halogens combine among themselves and form many compounds known as inter-halogen compounds of the type XX, XX3, XX5 and XX7, where one X is the larger halogen and the other is the smallest halogen. The anomalous properties of fluorine are: it is of the smallest size, it has got high electronegativity, it has got low fluorine-fluorine bond dissociation enthalpy and non-availability of d orbitals in the valence shell. Next, we will study about chlorine. Chlorine was discovered in 1774. Chlorine does not occur in the free state due to its high reactivity. It occurs in the combined states such as rock salt, NaCl, carnallite, sylvine, horn silver, etc. The most important commercial source of chlorine, which not only occurs as rock salt but is also found in plenty in the seawater. General methods of preparation of chlorine. First one is by oxidation of hydrochloric acid. By heating manganese dioxide with concentrated hydrochloric acid, chlorine is prepared. Equations: MnO2 plus 4HCl gives MnCl2 plus Cl2 plus 2H2O. The second one is by the action of hydrochloric acid on bleaching powder. The equation is CaOCl2 plus 2HCl gives CaCl2 plus Cl2 plus H2O. Chlorine can also be prepared by the action of concentrated sulfuric acid on sodium chloride in the presence of manganese dioxide. The equation is 2NaCl plus MnO2 plus 3H2SO4 gives 2 sodium hydrogen sulfate plus MnSO4 plus Cl2 plus 2H2O. The most important method for the manufacture of chlorine is by Dakin's process. It involves oxidation of hydrogen chloride gas by atmospheric oxygen in the presence of copper chloride catalyst at 723 Kelvin. The reaction is 4HCl plus O2 in the presence of copper chloride catalyst gives 2Cl2 plus 2H2O. The next important method for the manufacture of chlorine is by electrolytic process. Chlorine is obtained by electrolysis of brine solution, that is concentrated NaCl solution. Hydrogen gas is liberated at the cathode while chlorine gas is liberated at the anode. It is also obtained as the byproduct in many chemical industries. During the electrolysis, the oxidation taking place in anode is given by 2Cl minus gas, Cl2 plus 2 electron, and the overall reaction is 2NaCl plus 2H2O gives Cl2 plus H2 plus 2NaOH. Properties of chlorine. It is a greenish yellow gas with pungent and suffocating odor. It is about 2 to 5 times heavier than air. It can be liquefied easily into greenish yellow liquid which boils at 239 Kelvin. It is soluble in water. It is called chlorine water. It is a poisonous gas. Next, we will discuss the chemical properties of chlorine. Chlorine is a highly reactive gas and react with a number of metals and nonmetals. Combustibility. Chlorine is neither combustible nor a supporter of combustion. Chlorine reacts with a number of metals to form chlorides. For example, it reacts with aluminium to form aluminium chloride and reacts with sodium to form sodium chloride. Chlorine reacts with water to form hypochlorous acid. The equation is Cl2 plus H2O gives HCl plus HOCl. The hypochlorous acid is not much stable and decomposes to give HCl and oxygen. The equation is 2HOCl gives 2HCl plus O2. Chlorine combines with nonmetals to form chlorides. For example, P4 plus 6Cl2 gives 4PCl3. Chlorine has a great affinity for hydrogen. It reacts with compounds containing hydrogen to form HCl. For example, H2 plus Cl2 gives 2HCl. Chlorine reacts with excess of ammonia to give nitrogen and ammonium chloride. For example, 8NH3 plus 3Cl2 gives 6NH4Cl plus N2. However, if chlorine is also in excess, it forms nitrogen trichloride and the equation is NH3 plus 3Cl2 gives NCl3 plus 3HCl. Chlorine reacts with carbon disulfide and forms carbon tetrachloride. The equation is CS2 plus 3Cl2 gives CCl4 plus S2Cl2. In the presence of moisture, chlorine acts as a powerful bleaching agent due to its oxidizing nature. The bleaching action is due to the liberation of nascent oxygen. The equation is Cl2 plus H2O gives 2HCl plus nascent oxygen. This nascent oxygen reacts with the coloring matter present in vegetables and fibers and form the colorless substance, that is, it decolorizes them. Chlorine also acts as disinfectant agent due to its ability of killing germs and microorganisms. This ability is due to the oxidizing nature. It is largely used for sterilization of municipal supply water used for drinking purpose. Next, we will discuss the oxidizing nature of chlorine. It oxidizes ferrous salt to ferric salts. For example, 2FeSO4 plus H2SO4 plus Cl2 gives Fe2SO4 thrice plus 2HCl. Similarly, it oxidizes sulfides to sulfates. For example, sodium sulfite reacts with chlorine and water to form sodium sulfate and HCl. Chlorine oxidizes hydrogen sulfide to sulfur. The reaction is Cl2 plus H2S gives sulfur plus 2HCl. Oxidation in this reaction means removal of hydrogen. Similarly, it oxidizes sulfur dioxide to sulfuric acid. The reaction is SO2 plus 2H2O plus Cl2 gives H2SO4 plus 2HCl. Chlorine reacts with cold and dilute alkalis to produce a mixture of chloride and hypochlorite. For example, 2NaOH plus Cl2 gives NaCl plus NaOCl plus H2O. With hot and concentrated alkalis, it gives chloride and chlorate. For example, 6NaOH plus 3Cl2 gives 5NaCl plus NaClO3 plus 3H2O. With dry slaked lime, it gives bleaching powder. The equation is CaOH twice, that is calcium hydroxide, plus Cl2 gives CaOCl2, that is bleaching powder, plus calcium chloride plus water. Chlorine displaces bromine and iodine from KBr and Ka respectively. The equations are 2 KBr plus Cl2 gives 2 KCl plus Br2. Similarly, 2 Ka plus Cl2 gives 2 KCl plus I2. With saturated hydrocarbons, chlorine forms substitution products, while with unsaturated hydrocarbons, it forms addition products. For example, with methane, which is a saturated hydrocarbon, it forms methyl chloride. The equation is CH4 plus Cl2 gives CH3Cl plus HCl. It is called a substitution reaction because one of the hydrogen in methane is substituted by chlorine atom. Saturated compound means compounds having single bonds. On the other hand, unsaturated compounds are compounds having double bond and triple bond. In the case of ethene, that is an unsaturated compound having a double bond, addition products are formed. The reaction is C2H4 plus Cl2 gives C2H4Cl2, that is 1,2-dichloroethane. In the presence of sunlight, chlorine combines with several compounds such as sulfur dioxide and carbon monoxide to form addition products. For example, SO2 plus Cl2 gives SO2Cl2, that is sulfuryl chloride, and carbon monoxide combines with chlorine to form COCl2, that is phosgene, also called carbonyl chloride, and phosgene is a poisonous gas. Next, we will discuss the uses of chlorine. It is used for bleaching wood pulp, that is required for the manufacture of paper and rayon. It is also used for bleaching cotton and textiles. It is used in the extraction of gold and platinum. It is used in the manufacture of dyes, drugs, and organic compounds such as carbon tetrachloride, chloroform, DDT, and refrigerants. It is used for sterilizing the drinking water. It is also used for preparation of poisonous gases such as phosgene, tear gas, and mustard gas. Next, we will study about hydrogen chloride. Glover prepared this acid in 1648. In laboratory, it is prepared by heating sodium chloride with concentrated sulfuric acid, and the equation is sodium chloride plus sulfuric acid at 420 Kelvin gives sodium hydrogen sulfate plus hydrogen chloride. The HCl gas can be dried by passing through concentrated sulfuric acid. Next, we will discuss the properties of hydrogen chloride. It is a colorless and pungent smelling gas. It is easily liquefied to a colorless liquid. The boiling point is 189 Kelvin and freezes into a white crystalline solid. The freezing point is 159 Kelvin. It is extremely soluble in water and ionizes as given below. HCl plus H2O gives H3O plus Cl minus. HCl dissociates into H plus and Cl minus. The H plus again combines with the water molecule and form H3O plus, that is hydronium ion. Its aqueous solution is called hydrochloric acid. The high value of dissociation constant indicate that it is a strong acid in water. It reacts with ammonia to give white fumes of ammonium chloride. The equation is NH3 plus HCl gives NH4Cl. When 3 parts of concentrated HCl and 1 part of concentrated nitric acid are mixed, aqueous is formed, which is used for dissolving noble gases, example gold and platinum. Hydrochloric acid decomposes salts of weaker acids, example carbonates, hydrogen carbonates, and sulfides. Example, Na2CO3 plus 2HCl gives 2NaCl plus H2O plus CO2. Uses of hydrogen chloride. It is used in the manufacture of chlorine, ammonium chloride, etc. It is used to manufacture glucose from cornstarch. It is used for extracting glue from bones and purifying bone black. It is used in medicine and in galvanizing. For the laboratory preparation of hydrogen from a metal, HCl is used. The reaction is zinc plus 2HCl gives zinc chloride plus H2. It is used in the manufacture of dye and extensively as a laboratory reagent. When two different halogens react with each other, inter-halogen compounds are formed. They can be assigned the general composition XX-, XX-3, XX-5 and XX-7. where X is a halogen of larger size and X dash of a smaller size, and X dash is more electropositive than X. As the ratio between the radius of X and X dash increases, the number of atoms per molecule also increases. For example, iodine forms IF7. The size of iodine is larger than fluorine, and the ratio of radius between iodine and fluorine should be maximum. The general composition and examples of different interhalogen compounds are given here. Next, we will discuss about preparation of interhalogens. The interhalogen compounds are prepared by direct combination or by action of halogen on lower interhalogen compounds. The product form depends upon some specific conditions. Formation of some interhalogens are given below. Cl2 plus F2 at 437 Kelvin gives 2ClF. Cl2 plus 3F2 at 573 Kelvin gives 2ClF3. I2 plus Cl2 gives 2ICl. I2 plus 3Cl2 gives 2ICl3. General characteristics of interhalogen compounds. They are diamagnetic in nature. Interhalogen compounds are covalent in nature due to the low electronegativity difference between the halogens. All these compounds are volatile. Most of them are unstable, but none is explosive. The interhalogens are more reactive than halogens. This is because the XX- bond in the interhalogens are weaker than XX or X- bond in the halogens, except that of the bond formed between fluorine and fluorine. You can expect a question like this: why is ICl more reactive than I2? We have already learned that compared to halogens, the bond in interhalogens are weaker. That means this bond can be easily broken and new chemical bonds can be made. Thus, in the case of ICl, the bond between iodine and chlorine is weaker compared to that of I2, that is iodine and iodine. So, in general, interhalogen compounds are more reactive than halogens due to the fact that the iodine-chlorine bond is polar and weaker, while the iodine-iodine bond is stronger and polar. Structures of interhalogen compounds. The interhalogen compounds of the type XX- are very simple and consist of two halogen atoms linked together through a single covalent bond. Thus, this structure can be represented as XX-. XX- is used to differentiate between two halogens. X is a halogen and X- is a different halogen. The structure of ClF is given here. It is linear in shape. The interhalogen compounds of the type XX-3 possesses T-shaped down trigonal bipedal structure. It is formed by the sp3 dehybridization of the central atom X in its first excitation state. The compounds of the type XX-3 are BRF3 and ClF3. Interhalogen compounds of the type XX-5 has square pyramidal structure. They are formed by the sp3d2 hybridization of the central halogen atom in its second excited state. Interhalogen compounds of the type XX-7 have pentagonal bipyramidal structure. They are formed by the sp3d3 hybridization of the central iodine atom in its second excited state. Uses of interhalogens. These compounds can be used as non-aqueous solvents. Interhalogen compounds are very useful fluorinating agents. Chlorine trifluoride and bromine trifluoride are used for the production of uranium hexafluoride in the enrichment of uranium-235. Chlorine trifluoride and bromine trifluoride are also used as oxidizers and propellants. Inter-Halogen compounds are also used for the preparation of polyhalides. Due to the high electronegativity and small size, fluorine forms only one oxoacid HOF known as hypofluorous acid. The structures of various oxoacids of chlorine are given here. The in-text questions and answers of group 17 are given in the next part of the video.